Hello, everyone. Today, we would like to present saliency-aware foveated path tracing for virtual reality rendering. This work is completed in the State Key Laboratory of Virtual Reality Technology and Systems of the Beihang University and the Capital Normal University. Achieving a truly immersive experience in virtual reality requires high frame rates. However, rendering at such high frame rates places a tremendous burden on hardware, even on the latest GPUs. This limits the accessibility of VR technology for broader audiences. To address this challenge, researchers have turned to the human visual system for inspiration. Our eyes are not equally sensitive across the entire field of view. In fact, we perceive the highest level of detail only in a small central area called the foveal region. In contrast, our peripheral vision has much lower acuity, meaning we don't notice fine details outside the foveal area. This insight has led to the development of foveated rendering, a technique that dynamically adjusts rendering quality based on the user's gaze. By allocating high-resolution rendering only to the foveal region, we can significantly lower computational demands without sacrificing perceived visual quality. While foveated rendering is promising, traditional methods have limitations. They allocate resources based solely on the gaze point, ignoring the content of the scene. This can lead to noticeable artifacts in non-foveal regions, especially in areas that naturally attract attention, known as salient regions. The human visual system is content-dependent, meaning we notice details in salient areas even if they're outside our direct gaze. To address this, we need a content-aware approach that considers visual saliency. Our work aims to overcome these challenges by integrating saliency into foveated rendering, ensuring high-quality visuals across the entire scene. This is the focus of our work, developing a foveated rendering method that leverages visual saliency to deliver high-quality, artifact-free visuals while maintaining the performance benefits of traditional techniques. On this slide, we present an overview of the pipeline proposed in our article, which is composed of 4 stages. First, the geometric pass. In this initial stage, essential geometric data, such as surface normals and depth information, are gathered and stored. This stage also calculates the first intersections for path tracing, which streamline its process significantly. Next is the saliency prediction stage. Here, we estimate the saliency of each pixel, creating a saliency map that informs subsequent processes with geometric data and historical information. The third stage is path tracing. During this phase, we emit rays from the camera to compute pixel shading. While the first intersections are calculated during the geometric pass, path tracing handles subsequent intersections. This is where the saliency map becomes crucial, as it guides our sampling, ensuring that we allocate our limited resources effectively. Finally, we have the post-processing filtering stage. Given that path tracing often produces artifacts, especially in low-sampled areas, we employ a filtering process that adapts to the saliency map. This allows us to preserve fine details in high-saliency regions while reducing noise in less important areas. By tailoring the filtering strength to the saliency data, we maintain visual fidelity across the rendered image. To leverage saliency in our pipeline, one of the primary objectives is to predict saliency within the scene, which we then use to direct both path tracing and filtering processes. This prediction relies on an understanding of how the human visual system perceives saliency, which is influenced by 3 key factors. First, it is color. Color plays a significant role in how we perceive contrast. Areas with strong contrasts naturally attract our attention, making color a vital component in our saliency evaluation. In our pipeline, the color saliency is determined based on contrast with color histograms. Next is geometry. The geometric characteristics of objects in the scene also contribute to their perceived importance. Using the geometric data stored in our G buffers, we assign higher saliency values to obtrusive objects, which allows us to prioritize rendering for elements that will be most visually impactful. This factor is determined with the help of the Sobel operator. Finally, we have foveation. This concept aligns with traditional foveated rendering principles, which takes into account how visual attention typically decreases with eccentricity. By emphasizing areas within the foveal region, we enhance the overall visual experience in VR. By integrating these 3 components into our saliency evaluation, we can effectively guide the rendering process to optimize both quality and efficiency, ensuring that viewers experience the most engaging and immersive visuals possible. In this slide, we'll discuss the filtering stage of our pipeline, which consisted of a spatial pass and a temporal pass. First, the spatial filtering. Here, the image generated by path tracing is refined using spatial geometric information from the G-buffer. We draw inspiration from the edge-avoiding A2 filter and extend it with saliency-aware modifications. This filter operates through a weighted iterative convolution, where the weights are derived from 4 key components: the ray-traced image, surface normals, world coordinates, and saliency. Next, we have temporal filtering. After spatial filtering, we implement temporal anti-aliasing to further minimize artifacts like flickering. This process reuses historical shading results from previous frames by reprojection. A crucial aspect of this step is the blending weight, which influences how much we rely on previous frames. We've improved upon traditional methods by making this blending weight inversely proportional to pixel saliency. This adjustment ensures that undersampled regions receive more aggressive smoothing, while well-sampled regions experience minimal ghosting artifacts. In this slide, we present a graphical comparison between our pipeline and the others. The graphical comparison reveals that our pipeline delivers performance comparable to AISGR in foveal regions. In central regions, our method effectively preserves fine details and maintains image quality on par with AISGR. However, in peripheral regions, where the HVS is less sensitive, our algorithm consistently outperforms the others. This is also evident in areas with lower saliency, where our method reduces noise while maintaining perceptual quality. Specifically, our pipeline produces noticeably fewer noise artifacts in highly salient regions of the scene. For example, in the bistro scene, the red awning is rendered with greater clarity and less noise than the other pipelines. And in the San Miguel scene, the painting on the wall is also rendered with a cleaner, crisper appearance. These improvements in salient areas underscore the effectiveness of our saliency-driven sampling and filtering approach. We conducted 2 user studies to ensure the validity of our study. In our first user study, we aimed to assess the rendering quality of our pipeline against a reference image. Participants, after understanding foveal and peripheral vision, ranked images rendered by different pipelines: AISGR, Safarti, our method, and the reference. They scored each image from 1 to 4, with 1 being the lowest quality. Conducted over 3 scenes, 11 volunteers participated in the experiment. The average scores revealed that in foveal regions, our method and AISGR closely matched the reference, preserving detail where it matters most. In peripheral regions, however, our method significantly outperformed AISGR, showcasing its strength in noise reduction and visual enhancement. Chi-square tests confirmed that our algorithm's overall quality is statistically similar to the reference path tracer, but superior to AISGR and SFRT. This highlights our method's ability to deliver high-quality images in real time, leveraging a saliency-aware approach for optimal resource management without sacrificing visual fidelity. While our initial user study with static images validated our method's effectiveness, it didn't capture the full complexity of a VR experience. In VR, factors like camera motion significantly influence temporal filtering, impacting image stability and perceived quality. To address this, we conducted a supplementary user study in a VR environment to evaluate our pipeline's dynamic performance under real-world conditions. Participants then experienced the same VR environment rendered by 3 different pipelines. Afterward, they compared the experiences and rated their agreement with 4 propositions on a 5-point Likert scale, assessing overall rendering quality, foveal and peripheral region quality, and motion fluidity. One-sided Mann-Whitney U-rank tests were used, and the results showed our method significantly outperformed both AISGR and SFRT in overall rendering quality, peripheral region quality, and motion fluidity. Though our method also excelled in foveal region quality compared to SFRT, it performed similarly to AISGR in this aspect. Interestingly, our method received higher scores than AISGR in overall rendering quality, suggesting that peripheral artifacts, even if unconsciously perceived, affect rendering quality ratings. In conclusion, these results confirm our method's excellence in peripheral rendering and dynamic performance, making it an ideal choice for virtual reality applications. Our approach ensures superior image quality while maintaining real-time performance, even in the dynamic VR environment. In conclusion, we proposed a saliency-based foveated real-time rendering pipeline that can achieve perceptively similar rendering quality to a reference offline path tracer, which consists of 2 parts: a new sampling procedure dependent on content-based foveated rendering and path tracing algorithm. which can produce high-quality images in real time, and a filter algorithm that reduces visual artifacts to imperceptible levels when be used in conjunction with the path tracer equipped with the new sampling procedure. Thanks for your attention. Please don't hesitate to contact us if you have any further questions.